Hello children, welcome to Yavana's Physics. Today we had to discuss a topic, parallel plate capacitor. And what is a capacitance of a parallel plate capacitor? You know what is a capacitor? What is a capacitor? Two conductors separated by an insulating medium in between. And it is of various size, shape, etc. that we have discussed previous videos. Now in this video, we are taking a parallel plate capacitor. As the name itself is saying, it is two parallel plates with a small separation in between, and in that separation we have a dielectric or an insulator. This can be air, medium, mica, glass, etc. Okay, let us come to that. A parallel plate capacitor consists of two thin conducting plates, parallel plates, each of area A, each has an area capital A, held parallel to each other. They are set parallel, one is placed parallel to the other and at a distance d apart. The separation should be small, that will come later, so the separation should be a small one, d, with dielectric or insulator in between. Dielectric is same as saying insulators. So come to the figure, we have two parallel plates, number 1, number 2. First what we do is take a plate 1 and give it a positive charge. So we are bringing a positively charged plate, that is plate 1. Now with a small separation d in between, we have another plate 2. So what happens is, due to induction, the inner side of the plate 2, which is facing plate 1, gets negatively charged. Why? The free electrons are getting attracted to the inner side of the plate 2. And at the same time, the protons are repelled, or the positive charge is repelled by this positive, and it comes outside the second plate. And the second plate is grounded. So all the positive charges which are coming out of the second plate, or the outer surface of the second plate, is attracted through the ground because it is grounded. And you know what is grounding or earthing? It is just taking the electrons. The electrons from the ground moves towards the plate and gets neutralized. So you have charges only well inside the plates, nowhere outside, inside the plates. So if suppose you are taking two plates, it is arranged in this manner. So if you can take this as a parallel plate, this another one, you are placing it such a manner that this line is visible to you. So this is what I mean, that plates are placed in this manner. So this inner part positively charged, this inner part negatively charged. So placed parallel to each other. Now what happens? When they are in this manner, you know, this is positive and this is negative. There is an electric field which is directed from positive plate to the negative plate. So the direction is uniformly spaced lines parallel to each other, shows that the field is quite uniform. And this having plus q charge, this having same minus q charge. Whatever be the plus q, the same minus q. So we have studied a term known as surface charge density. In Gauss's law, we have charge distribution, there line charge, surface charge, volume charge. So you have a term surface charge density given as sigma is equal to q upon A. So what is q? Q equal to sigma A. This previous knowledge we need. Okay. Now come to the equation. What is C? C is equal to q upon V. And in the place of q, you give the equation sigma A, substituted for q as sigma A. Now another previous knowledge we need is E equal to minus dV by dr. What do you mean by the minus dV by dr? Negative gradient of potential. And the negative sign shows that electric field has a direction in which potential reduces, that is dV by, means with respect to distance, potential is getting reduced. That reduced direction, that decreasing direction is that of electric field. When you look at the figure also, it's very clear. The potential is decreasing in this direction. This is positive plate, this is negative plate. So the reduced potential is from left to right. So the electric field is also from left to right. Okay. So from that you can have E is equal to V by D, where V is the potential developed between the plates and D is the separation between the two. So E equal to V upon D. So what is V? E into D. Substituting for V as E into D, this equation will be like this. Now again one more recap. E is equal to sigma by epsilon, where this is a parallel plate. So again in Gauss's law application we have studied. Here the electric field is 0. Here the electric field is 0. Here it is equal to sigma by epsilon 0. You can go to the Gauss's law videos. You can check how it comes as sigma by epsilon 0. So E is equal to sigma by epsilon 0. Substituting for E, sigma by epsilon 0. Sigma and sigma cancels. Epsilon 0 go upside. So you have the equation epsilon 0 A by D. Means it depends on three factors. Number 1, epsilon naught or epsilon 0 A by D. Epsilon 0 refers to what? Permittivity of air in this between, or the medium here is air or vacuum, where you take as epsilon 0. If it is other than air or vacuum, instead of epsilon 0 you use the term epsilon, that is epsilon 0 epsilon r. So if it is for any other medium, the value will be depending on epsilon r or dielectric constant. And A, as A is increasing, bigger the area of the plate, capacitance increases. So this is why I told you the distance should be small. When D is reduced, capacitance increases. The capacity to store the charge also increases. So the required condition is A bigger, D smaller and epsilon 0. If it is having no other medium, if there is some medium, there is a term known as epsilon r. Obviously r is greater than 1. Therefore, when you have placed this thing in an intervening medium, capacitance goes up. So these are the factors on which capacitance depends, and it's very clear it is not depending on either Q or V, because in this equation you can see that no dependence on Q or V. Okay, hope it is clear. You could understand whatever I have mentioned. If there is any doubt, please put in the comment box. Definitely I will be responding for the same. So thank you for listening. Thank you.